your FEA simulation is completed. Abacus is showing very beautiful stress and deformation results. But the real question is, can you trust those results? In this video, let's find out how to validate our FEA results using 3 simple checks. Let's start. So we have a rectangular plate of length 100 mm and a height 50 mm containing a centrally located elliptical hole. The plate is subjected to an axial tension load of 2000 newtons at one end, while the opposite end is fixed in all degree of freedom. We have already completed this analysis in Abacus. Now the important question is, how do we know whether our analysis setup and results are correct and reliable? To check this, we are going to validate our FEA results using 3 important checks. The first one is deformation, the second one is reaction force, and the third one is stress and mesh convergence. Let's start with deformation check. Click on results. This is our analyzed model. Before checking the results, let's first verify the applied boundary condition and loading. Go to load, click on load manager, click on edit. If you see here, one end is fixed in all degree of freedom and on the other end we have given a load of 2000 newtons. Now let's check the deformation. Go to visualization. Since we applied a load in x direction, we need to look at the displacement in the x direction. Click on U, click on U1. Since we applied a 2000 newtons in x direction, the plate should deform and extend in the direction of the applied load. Let's move this to step 1. So we applied the load in x direction and the plate is deforming in the same direction. So this is our first validation check. So the second check is reaction force. We applied a load of 2000 newtons to the model, but how can we confirm that the complete 200 newtons load has actually been transferred through the model? For this, we need to check the reaction force at the fixed locations. To do this, go to create XY data, click on ODB field data, click on continue, click on RF1, click on elements or nodes, click on node sets, click on highlight items in viewport, select the sets. So this is the set 4. So this is where we fixed all degree of freedom. Click on save as. Since we have a lot of nodes, we need to sum. Click on sum. OK. Dismiss. Now click on data manager. Select this. Click on plot. Dismiss. As you can see from the plot, the maximum reaction force is approximately 2000 newtons. Double click here. You can see 2000 newtons. Therefore, we confirm that the applied 2000 newtons load is being correctly transferred through the structure and balanced by the reaction force at the fixed boundary. So this is our second validation check. Now let's move on to third important check, stress validation. Click here. Click on stress. The question is, how do we know whether stress value obtained from the simulation is reliable? The stress result is strongly dependent on mesh size, especially around areas with stress concentration such as elliptical hole. Therefore, we need to perform a mesh convergence study. For each element size, we obtain a different max stress value. In this model, let's go to mesh, click on seed part. So in our initial model, we used the element size of 3 mm. For 3 mm mesh, we obtained a max stress of approximately 81.47 MPa. Let's record this. For 3 mm, we got a stress of 81.47 MPa. Now what we will do is, we will reduce this mesh size to 2 mm and we will check whether any difference in stress we will get. Go to mesh, click on seed part, change this to 2 mm, click on OK, delete meshes, click on Mesh part, yes. Go to job, click on submit. Okay, submitted. Completed, click on results. Click on XY, click on contour. So for 2 mm, the stress increased to 88.65. So for 2 mm, the stress increased to 88.65. So the percentage change is 8.8 percentage variation is there. Now we will check with 1 mm. Go to mesh, change this to 1 mm, click on OK, delete mesh. OK the mesh part. Go to job, submit. OK. Completed, click on results. Click on XY, click on plot contour. See, for 1 mm, the stress increased to 93.31 megapascals. 93.31 megapascals. And the percentage change is 5.3 percentage. Now we will check with 0.5 mm. Go to mesh, click on seed part, 0.5, OK, delete mesh. Mesh the part, yes. Go to job, submit, OK. Completed, click on results, XY, plot contour. For 0.5 mm, the stress increased to 95.39. 95.39. And the percentage change reduced to 2.2 percentage. Let's check with 0.4. Go to mesh, change this to 0.4. Click on OK. Mesh it, yes. Click on job, submit. Status completed, click on results. Click on XY. Click on plot contour. The stress is 96.04. 96.04. And the percentage change reduced to 0.7. So we will check for 0.3. Click on mesh. Click on seed part. 0.3. Click on OK. Delete mesh. Click on mesh part. Yes. Go to job. Submit. OK. Completed. Click on results. Click on XY. Click on plot contour. And the stress is 96.61. 96.61. Now let's compare the results. So when you compare 3 mm and 2 mm mesh, there is a difference of approximately 8.8 percentage. When we reduce the mesh size from 2 mm to 1 mm, the difference decreases to approximately 5.3 percentage. As we continue refining the mesh, the change in max stress becomes smaller. Between 0.5 and 0.4, the difference is very small, which is 0.7 percentage. This indicates that the stress result is approaching a stable value. Therefore, we can consider the mesh to be considered in this range, and the corresponding element size can be selected for this analysis. So here you can go with 0.5 as our standard mesh size, because after this the variation is very minimal. So we should not simply select a very coarse mesh such as 3 mm, because the stress value is still changing significantly as you refine the mesh. This process is called mesh convergence study. So to conclude, there are 3 important checks we can perform to validate our FEA results. By performing these checks, we can have much more confidence that our FEA model is correctly set up and that the simulation results are reliable. I hope you understood these practically FEA validation checks. Thanks for watching. By the way, I also created a complete Abacus CAE course on Udemy, where I cover these concepts in detail along with practical simulations. The course covers linear analysis, nonlinear analysis, dynamic analysis, along with many other important Abacus CAE topics. If you're interested in learning Abacus CAE in practical way, you can access the course using the link provided in the description below. Thank you for watching.